column design, we have we all know that vertical cooperation members are termed as column, and this column that we're talking about, the loading may be, at times it might be centroidal, that is loading at the center of it. That's axial load. And when the load is along one axis, that's concentric load. But when it is along two different axes, that's eccentric loading. That is when it's not acting through the centroid. Though this one is acting through the centroid in one, as you can see here in this diagram. This is the axial loading. This is uniaxial loading. It's along the ES component, while this one is not on ES or EY. It's just one side. That's biaxial loading. Now this beam loading, we need to know the major and the minor axis. And supposing we have this column 400 by 200, and we need to find the major axis and the minor axis. This is very simple. We just use our formula BD cube over 12. Now, considering along the S plane, the B is 200, the D is 400. So we'll calculate the moment of inertia. We have this, and likewise, if it is along the y-axis, so definitely along the y-axis, that means this side will be our B and this side will be our D, or just interchange it. So it will be something like dBq over 12. So we have this along the y component, the moment of inertia along the y component. Now, the task I want the class to do, though I'm not with you, I want you to carry out this. Calculate the major axis and minor axis of this column that is shown here, given that it is 200 by 450, and the breadth is 200, and the depth is 450 mm. So kindly do that, and I would like to see that in before our next class. Please take note, class. This task A must be done. Now, the axis which is perpendicular to the depth of the column is termed as the major axis. What do you mean by perpendicular? When I say this, let's say this is the depth, the perpendicular axis to it, that is this perpendicular to this. So it's termed as the major axis, while the one that is parallel, this parallel is parallel, this parallel is termed as the minor axis. So that's just the short history. So we have the bending axis. Maybe it's bending along the S or Y component. I don't need to talk about that. Now I want you to look at this this floor plan, and all these ones are columns in the, or the footings, the column footings in the plan. Now I want you to look at it. If you look at this, I want you to tell me, maybe it is axially loaded, maybe it is eccentrically loaded or concentrically loaded. I want you to do that. But let me look at this. Let me just explain this. Now, looking at this this particular one, looking at this, as I said the other time, that it is almost impossible to have a centrally loaded column. Now, for this particular one, you can look at the look at the span. It's loaded the same span here, the same span here, the same span here, the same span here. So this one, these red ones, or these red columns, they are axially loaded. However, let us look at a condition where it is okay, let me just read what here. Due to rigid frame action, lateral loading, and practical aspect of construction, there will be a bending in all the inside columns too. The inside corner, the side and corner columns we have shear along with axial loading and bending. I don't think we need to talk about that. Now let us look at the middle columns in the end row. Middle columns in the end row. This in the this is C2. I don't know about C2 here. C2. You can see that this one is uniformly loaded to this side, but this other side is not loaded. So it is that one is treated as eccentrically loaded, sorry, concentrically loaded, or the load is applied. It is applied on one of the, let me say, on two of the axes, but it's not balanced with the other one. However, if you look at this one, it is eccentrically loaded. What I'm trying to say is that there will be moments. If you look at this, if you look at this particular C2, if this particular span, if it want to cause it's being balanced by this other span, so there won't be movement along this span. But looking at this one, because this one is not balanced, there will be movement along this section when it's loaded. Now that's why it's just in one way, or it's concentrically loaded. But however, when we have it in this condition like this, it like this C3, it is not loaded on this side and it's not loaded on this side. That there's movement in this direction, movement based on this span, movement based on this span. That seems to have two movements, or okay, two bending moments taking place. That is movement along the x-axis and movement along the y-axis. What it means is that it will be biaxially loaded. That is an example of a biaxially loaded column. While this one we only have for just along this plane, which is your x-axis, it is just a uniaxially loaded column. So I want you to look at that. Now tell me, based on this plan below, you also attend this one. Tell me whether it is the axially loaded column, the column that is related to uniaxial bending, and the one that is related to biaxial bending. So you let me know. I think there's not too much I need to say about this. You can always read this one. I say to you that a column can be classified as short or slender. It can be classified as a brace or unbrace, depending on the various dimensional and structural factors. Now, when we say a column is short or slender, there are some conditions that we need to check to be able to say this column is short or is slender. I will explain to you as we proceed. Now, a column cross section can be provided that can be used, provided that the greatest overall cross sectional dimension does not exceed 4 times its smaller dimension. That is, your h is less than or equal to 4b. So now let us look at short and slender columns. When I say short and slender column, how do we know which column is short, which one is slender? Now let us look at this. A column can fail in one of these ways. That is, maybe due to compression of this concrete and the steel, maybe due to buckling, that is, it's about to twist, or maybe the combination of twisting and compression together. That those are the kind of ways you can see a column failing. Now let us look at when the ratio of your effective height to the major axis, when it's your effective height related to the major axis is less than 15, that means it is a short column. But when it is greater than 15, that means it's a slender column. Now let us look at okay, for instance, this your LES is your effective height in relation to the major axis, and LEY is your effective height in relation to the minor axis, while your B is your width of the column and your A is the depth of the column. A column, when we say a column is braced, that means when there is a lateral load acting on it, the column resists this lateral load by other elements in the structure. Maybe we introduce a shear wall or other form of bracing, like you always see. Okay, like when you have a cross, when you look at a right tank, standing tank, you see that there's always a bar like cross in between the beams supporting the bracing supporting the column. Those are your bracing. And when we have a situation whereby there's no bracing, and the structure when there is lateral load, that is when there's wind load, is being resisted by the bending action of the member, that is an unbraced column. So I think this depth end condition, the end condition of that is how the end of the column are connected is very important. The depth of the beam that is connected to it, the depth of the column itself is very important. And we have it fully restrained, that is head down, very elevated, head down tightly together. Um, and the depth of the beams is greater than or equal to the depth of the column. This is the beam, this is the column. Then we have a situation of end condition 1. But when the depth of the beam is less than the depth of the column, like we have here, then we have it is partially restrained and end condition 2. However, when there is a nominal restraint between the beams and the column, maybe it looks as if it's simply supported, as you can see here, as if it's simply supported, then we have a nominal, and that is nominally restrained. That's end condition 3. Now all these conditions, there's a bit they are used for the beta value of a column, as you can see in your table 3.19 of 8110. If the end condition 1, maybe let's say this is the top, this is the bottom. So if the top is end condition 1, the top of your column, if it is end condition 1, and the bottom of the column, if it is end condition 2, you just do 1 and 2. You look at the value and pick it for your beta value. So this beta value is used to calculate our effective length and effective height rather. But as we look at an example here, we have it this way. Looking at this structure, we have our height to be 250, our height to be 350, and the spacing along the x-axis is 4 meter, while from this side to this along the y-axis is 4.4 meter. Now if you look at it from this side, you can see the height, but if you look at it from this side, you see that the height we'll be talking about will be from here. Now those end condition, when we look at it, LES over LEY, that is LES over LEY, LES over H, or LEY over H, we look at the value that we arrive at, and the end condition will let us know the beta value we take. So when we apply this formula, then we have a value. This value is what we are trying to check whether a column is slender or short. When it is greater than 15, then it is not short, but it is slender, as you can see here from this condition here. So just look at I want you to look at this section. You group yourself into groups given this particular sizes and this slab thickness based on this diagram. I want each person to help me to tell me whether the column is short or is slender using these values. So you should be able to earn this diagram. So where you have LOS, LOY, you just put the value of LOY there, and LOS, you just put LOS. You put this there, then you calculate it out. Let me see what you have. As I told you, there's a governing rule concerning column, just like I explained last week, that the longitudinal steel, we will look at, I said it's a minimum of 4 bars. A minimum of 4 bars is required in a rectangular column. That is, when you're designing a column, it is wrong for you to be using 3 longitudinal bars, those standing bars. It is wrong for you to be using 3. The minimum requirement is 4 bars, as you can see. And for a circular bar, the minimum requirement is 6 bars. It's very important. So when you are trying to write your structure, when you are dealing with a rectangular column, the minimum number of bars is 4. So and the size of this bar for these columns should not be less than 12 mm. It's very important, please. So now the area of I think I've explained this one. The minimum area that is respected, 100 AS over acre, should not be less than or equal to 0.4, and it shouldn't be greater than 6.0 in a vertically cast column and 8.0 in a horizontally cast column. When we have it vertically 6.0, horizontally we have it 8.0. Now, but at labs it shouldn't be greater than 10. Now, this 100 AS over acre This AS, as I told you, is the area of reinforcement, while this A call is the area of concrete, or area of your column, area of your column, area of your concrete column. Now let us look at I have explained this to you, the links, the minimum size of the link. I've explained this one quarter size of the largest longitudinal bar, but not less than 6 mm. I've explained this in the last class. So, and the maximum spacing should be 12 times the size of the smallest reinforcement bar, and I told you that it shouldn't be greater than a particular figure, which is 300 mm. Now, the link should be arranged so that every corner bar and alternate bar or group in an outer layer of longitudinal steel is supported by a link passing round the bar. Now, the way we arrange our reinforcement, you see that we just have what's it called? We have some people will just use let me come in. Some people will just I wish to draw, or do I have, okay, I don't know, okay, I don't have a diagram for it. Okay, I think I have it at the end. Let me just show you at the, I think I should have it at the end. Okay, now look at this. You can see this is the way your links should be bent, not that you just put it just bend it anyhow. This is the way the angle 135 that is referred to. You can see it. This one will be held bound very well correctly. So these are the way you do your connection of your link for your columns. So let me continue with what I was discussing earlier. So I said it's 135 degree, not greater than 135 degree. All the bars or group must be restrained by a link within 150 mm. I think I've explained this. Now, axially loaded column. When you say a column is axially loaded, that is, the loading is acting directly on top. Now, when we look at the stress, this is the formula for the stress based on the steel and the concrete, and this for the concrete, this for the steel. But however, because there's no perfect condition, so there will be room for movement and some other things. So we apply this 0.4 n equals 0.4 SUBH plus. This is for a rectangular column, while this is the general one if it's for any column, but for a rectangular column we use this formula. Now let us look at example of how we apply an axial load on a column, and how we calculate the area of reinforcement. Now, supposing we are given that we are to design the longitudinal reinforcement for a 300 mm square column that supports an axial load of 1700 kilonewton at the ultimate limit state, that the characteristics material strength, that is your Fy, is 460 Newton per mm square, and our FCU 30 Newton per mm square. Now I want to calculate, what are we trying to calculate? We want to design the longitudinal reinforcement. This is what we are interested in. And I told you, because this is a square column, it's just a square is a rectangle too. So we're going to use this formula, n equals to 0.4 SUBH. This formula, you can see this one is in your BS 110, equation 38 of your BS 110 that I sent to you earlier. You will see it there. Now, our axial load given is 1700 kilonewton, which is this, and our 0.4 is this, our B FCU is this, our B is this, our H is this, our ASA like that, substituting Fy 460 this. Then you have your area of, because by the time you move this one to this side and you calculate your AS, you are going to get AS equals to this. Now look, using your table, somebody will ask, why I say provide 40 25 bars area of 1960. I've explained to you that when we have this condition, we'll go and look at this is the minimum reinforcement that is needed. So we'll go to our steel table and go and select, based on the area, the number of bars that we will need. Now if you look at I also explained to you how to calculate it manually. Let me see if I have the table here. Okay, I don't have the table here. I think I've used it before. Okay. The table. I think I sent the table. I asked you to screenshot the table in your last class. Okay. Okay. This was spacing. This was spacing. This one is for the spacing. When we're treating slab, it's different from the for the one for number of reinforcement bar. So I think I gave you in your last if you check your WhatsApp group, it should still be there. So you just look at it, the number of reinforcement, and then select what is appropriate. Now, if you calculate it, I told you how to calculate it using pi r square, how to get a unit number, then you can divide it with what you have, then you multiply the number that will be able to get to the next area of reinforcement. Because somebody having 1741 square as the minimum area of reinforcement, if you go below this, that means you want the structure to fail. So you should go to the next one that is higher than this. That is why we are using 1960 square in that table. Those of you in class, you should be familiar with that table. You can just open the table and then you will see what I'm talking about. Now, uniaxial bending. When we say uniaxial bending, now this one is very important for us, as I explained to you. When the column is having when the column is subject to axial load and uniaxial moment. Now, the procedure, it says that we'll calculate our n over bh and m over bh square, and then we'll use the necessary chart to consider, let me say, to know the number of area of reinforcement that we will need. It's different from this axial loaded column where we have a simple formula that we use, but for this particular one, we're going to be using our chart, column chart table for that. Now, let us look at an example, and okay, and then we'll check appropriate percentage of reinforcement too. Now let us look at an example. Given we want to design a longitudinal and shear reinforcement for a 275 square column. Now, and we are told that the first condition is that the ultimate axial load is 120 and 1280 kilonewton, and the moment along the x-axis is this. While the second condition is we have a axial load of this, and the bending moment is 35 kilonewton meter along the x-axis and 25 kilonewton meter along the y-axis. Now let us look at how we treat this. Given that we have our SCU to be 30 Newton per mm square and Fy to be this, and the cover of reinforcement is this, what we just need to do in this condition is to calculate our n over bh and m over bh square. So for this one, we have m over bh square to be this, where our m, which is our moment, m over, and our b is this, because it's a square column. B and h is 275, so we have it bh square. Now we have it as 3 here, and our n over bh, where is our n? This is our n, our axial load is n, which is 1280 over bh, we have it as 17. So what we are going to do is that we try to look at d over 8, d over h rather, but because we don't have we don't know what our d is, we take it from this one, then we deduct the necessary reinforcement and cover, that is half of reinforcement and the cover, to get our effective depth d. Now let's assume we are using 20 mm diameter bar, and the diameter of the links is 8 mm. So for this particular one, we can say, okay, our 275 minus cover is given, I think cover is okay, let's say cover is 35 here, minus 35 minus 20 mm minus 20 over 2, so sorry, minus 8 mm minus 20 over 2. This is for the link, this is for the reinforcement longitudinal bars. Now, so we have it as 222 for our d. So we calculate our d over h, that's 222 divided by 275, we have it at 0.8. Now this 0.8 is needed for our chart. Now if you look at the chart, there are many charts in that chart table, and it's also referred to as interaction chart. Now I think it should be in the next page. Okay, now looking at this chart, this is the way it is. We are going to look at it first. Is this condition met? FCU, you see 30, is Fy 500, then d over h. All these three conditions must be met before we can use this chart. However, how do we use this chart? You can see from this chart that we have m over bh square and n over bh. So all we just need to do is look at what's the value of our m over bh, which is 3, what's the value of our n over bh, which is 17. So we move 17 here, and 3 here. You can see where this red value is. It's meeting at this point here. Now, how do we now do it? When it's meeting here, what it means is that we are going to now use this, the way you use this chart, you look at this. That is what we're going to use to calculate our 100 AS over BH. Now, for this particular one, if it is 0.4, I will use this one. If it is 1, if it is 2, and if it is 3, this is the one for 3, and you can see it's touching 3. So what it means is that my 100 AS over BH is 3. So that is what I wrote here. 100 AS over BH is 3. So from this formula, I can now calculate my AS to be equals to 3 times BH over 100. That's 3 times BH over 100. Then I have my AS to be this. So from this, I can now go to the steel table and then provide the number of H20 diameter bar that I will use for this design. So if you look at the table, the number of 8 is 8 number of 20 mm diameter bar that we need. So I'm providing 2510 mm diameter bar, square diameter bar, which is area, sorry, 2510 square area of reinforcement, which is higher than this. And then we will now go to the links. I told you that the link should be a minimum of quarter of the diameter of the longitudinal longitudinal bar, that is 1/4 of 20, and that is 5 mm. But you were told that the minimum acceptable link size is 8 mm, so I will provide 8 mm diameter bar for this. Now the spacing, I said is 12 times the diameter of the smallest longitudinal bar, that is 12 times 20 also, so I have 240. However, or the smallest cross-sectional dimension of the column of 275. So for, I think this 275 is the maximum provided for here, but 300 mm is the maximum that is acceptable. That the maximum, but for this particular one, since we have 240, we use 240. So, or the smallest cross-sectional dimension of the column, okay, 275 mm. Now we use 240 because it's smaller than this, so we just provide it at 240 mm center bar. Now, saying we are providing eight number. So how are we going to arrange it? This is the arrangement format of our column. You can see the way it is. You can see the way it is bent here at 135 degree. So we are providing 4 at the top, 4 at the bottom, and then these are the links. And they are 8 mm size and space at 240 mm spacing. So this is how you interpret it graphically when you are drawing when you are trying to draw your reinforcement detail for this particular column. Now let us look at the condition B. That condition B, we said the ultimate load is 1280 and the bearing moment is 35 along the x-axis, 25 along the y-axis. How do we treat such a condition? We come here also, we calculate we already know what our B prime is. Okay, we can calculate our B prime and our H prime. Now, since we have this condition, 25 mm bar, 8 mm link, now we can calculate our B prime from our H prime. From our H, that is when we remove half of the diameter bar and the link and the cover, just like we did the other time. We have 220 mm. Now, what we are going to calculate this time around is we are going to look at ms over my, and then we're going to look at h prime over b prime. Now, your ms over my is 35 divided by 22. That is the moment along the x-axis and the moment along the y-axis given. 35 divided by 25. You calculate that, then you now look at that condition. Is it greater than h prime over b prime? If it is yes, then we are okay. If it is no, then there's another thing we'll do, but I will explain when we get to that condition. Now, the next thing we calculate is we calculate our n over bh fcu. We have it as this value. Now, what do we do when we have this? Now, in this table, we need to get our beta value, and to do that, we have it. Maybe we look at this n over b squared. What is the value along this side? We have 0.56, so it's between this place and this place. So our b prime, we interpolate it to get the value that will fall in between this 0.30 and 0.42. By interpolation, it falls at 0.35, this b prime. Now, when we get our beta to be b prime, then we now calculate our moment about x axis, which is m prime s, and our moment along y axis. Now, for the formula moment along x axis, m prime s, this is the formula for it. M prime s equals to ms plus bh prime over b prime my. Now, where did we get this one from? Let me take us to, I think I need to take us to our design manual. Our BS 8110 is very important now. Let me just go to the code. It's very important I take us to the code now. This is the one, table 322, that we used the other time to calculate our beta, and this is the formula I was talking about. So I think I should just relate it to the note. So for this equation, I think I should bring it out. Let me just write equation 40 basic 110. And then the other one is for the y-axis equation. I want you to look at this one. You can see that they look almost the same. However, this one is calculated for your my prime, while this one is calculated for your ms prime. You can see the condition to use this: if this is greater than or equals to my over b prime, while this one if it is less than my over b prime. So you calculate the value, but let us look at this. Ms over h prime, ms over, okay, let's calculate our ms over h prime and my over b prime. This one is greater than, okay, okay, I think I just want to step for you people, but this is the condition: ms over h prime and my over h prime. We look at it, we look at the criteria. Just calculate your ms. 35 divided by, we have 275 for the, okay, sorry, 220 for the h prime. 35 divided by 225 is it greater than 25 divided by 220? Definitely this one will be greater than this one, will be greater than this. So that's why we are taking this. So now for this one we have 35 plus beta. I told you how we got this beta here, and then we calculate, put the value, just substitute the value, this one to this, the h prime this, b prime this, then my is this, calculate it, you have this one. Now you calculate the m prime x, then over ba square. Now, just like our m over ba square that we did, so instead of using m over ba square, we'll be using m prime s over ba square. So for this particular one, we have, but if it is this condition, this other condition, if maybe it's my that is greater, then that is what we're going to use here. So for this particular one, we have it as we have 43.8 times 10 raised to the power 6. That's the value we have here, divided by this then we have 2.1, and our n over bh is 17. So we go to the table again. After calculating our d over h should be 0.8. We go to this table again. This table, we look at 2.1 and 17, 2.1 and 17, where they are meeting. Now look at this one. It's around 0.4, 1, 2, around 2.3, 2.2 something. Now you just say our 100 as over bh equals to 2.2, then you calculate it out, then you have this. So from this you can get the number of 25 bar that will be needed. So that is all about that. Then you can calculate the links and the spacing, then you are done with that. Now sorry, yeah, okay, it's here. Now I'm done with that. Now I want us to look at this task again. I want you to practice this. Just please practice this class task to I think that you say to be just class practice this, and then calculate your m prime s and m prime y, and let us see what we have. So I think that's all about Biaxial bending, Uniaxial bending. So what else do I need to, others are things you can read on your own. So that is all I need to explain to you on this particular column bending. So for the assignment, let me just extract the assignment out. I think I should extract the assignment out. So you were told to, sorry, for the assignment we have this. Then we also have I have this. So I'll be collecting it on or before 20th of June. So, and we have I think there's one more. Yes, this. Okay, one more. I think one more. I think I should have one more. Okay, so that is all. I will want the assignment before 20th. So if you are with me, I will send a link to the governor now at 9:10. So the link will stop working at 9:30. So I want you to take that test and do it as soon as possible. And I wish you all a wonderful time. Have a lovely day. I will contact the governor on WhatsApp now. Thank you very much.